Okay, so last lecture we saw functional programming. This time we're going to see logic programming or prologue style programming, which is another idiom that is also supported by Lean and generally by most proof assistants. But in proof assistants, they're called inductive predicates. But this resembles very much the horn clauses of prologue, if that tells you anything. And if it doesn't, then it doesn't matter because I'm going to cover the material, assuming that you don't know it. I'll just mention in passing some correspondence, right? So now we have a more complete picture of Lean. Lean is functional programming plus logic programming, so which is really just a phrase that means prologue and similar languages. I think datalog is one of them. And then more logic, you know, like arbitrary quantifiers, arbitrary connectives, you know, in various combinations as we've seen before, and lemmas and proofs and so on. Okay, so we start with some examples because in my experience in previous years is that it's good to see inductive predicates in various contexts, so various forms of inductive predicates before you really develop an intuition about what they're all about. So we'll see first 4 examples where they more or less make sense. You know, you would use an inductive predicate in those contexts in a proof assistant, or at least could reasonably do so. So they're fairly realistic examples, and they're also quite varied. But the basic idea is that inductive predicates are useful when what you have is not necessarily a function, where when you have what you have is a you know, you might have a transition system where you have several, you know, non-deterministic transitions that are possible, and then you cannot just have a function that returns the next transition. You have to have a relation that models, you know, everything that's possible. So you might have, you know, non-determinism, or you might have non-termination, and then, you know, again, functions are not ideal. Predicates are better for those cases. We just want to model something that happens to be a predicate, like the even predicate, right? So a mathematician might write something like this, you know, the set E of even natural numbers is defined as the smallest set closed under the following rules. So 0 has to be in that set. And for every natural number k, if k is in the set, then k plus 2 must be in the set. So most of you probably have seen such a definition before in your life, a kind of closure, the small set following a certain number of rules. And this is basically the pen and paper version of an inductive predicate. And the key is always the smallest, right? Because you could say, oh, E is the set of all natural numbers, and that is closed under both rules, right? 0 is in n, and k plus 2 is in n. But that's not the one we want. We want the one where 1 or 3 or 5 is not in there, right? So we want the smallest set. We just want to have the even numbers in there and nothing else, no junk, if you like, right? And so this is how we define it in Lean. And again, I know from experience that this syntax confuses people quite a bit. But we're going to go very slowly here. This says we define a predicate, right? So it's a bit like, the first line is a bit like def, but the syntax has the keyword inductive instead. And inductive just means smallest, right? So if there's also a concept of co-inductive, and that means greatest. But here that we're dealing with smallest for the reason I just gave, right? So this is the type signature, that's fine. And then we basically have an enumeration of the cases we want to have. This is the name of the rule, and so it's the name of a lemma, if you like, and this is the property. So we want to have that 0 is even, that's the first rule, and then we say for all k, if k is even, then k plus 2 is even. And you see that's the second rule. But instead of calling them 1 and 2, we call them 0 and add 2, because that's more like programming-like or something. So one way to parse, you know, to understand this definition is, I'm going to write it a bit differently. Namespace temp, right? It's just temporary. And so I'm going to use concepts we already know. So we know constant to declare an arbitrary symbol. We know axiom to declare an axiom, and here's another axiom. Actually, I can leave it like this. So this would be another way to look at it. That would introduce also predicate even. It would honor rule number 1. It would honor rule number 2. There are two problems with this, axiomatization, or with this approach. Well, the first problem is that axioms are always dangerous, right? So we could mistype something and then we could maybe prove false afterwards. So we should, as much as possible, never use axioms. So that's the first problem. The second problem is that this captures the fact that that the set is closed under these rules, but it doesn't say that it's the smallest set, right? So there's nothing that tells us that 1 is not even. There's also nothing that tells us that 1 is even. So we couldn't prove one or the other. But with this definition here, we'll see later, we can actually prove that 1 is not even. Because of the word inductive, Lean knows that this has to be the smallest set or smallest predicate, and therefore it will do the right thing. So this version we're not going to use, but you see, if you have problems remembering the syntax, just remember the first line is like constants, and these are just like axiom. You just have to replace the bar with axiom. And then, that will help give you the right idea of what you need to put where. I mean, this is the name of the axiom or the name of a lemma. This is the usual column, and so on, right? I should mention here, I'm going to give a very operational or lean-oriented view of inductive predicates, but in the Hitchhiker's Guide, you're going to see a bit more theory or different ways to look at them, as least fixed points, among other things. And then, for some of you that might be helpful, understand a bit more what happens or why lean does certain things. Yeah, well, it's actually to some extent it's something that that I expect you to learn, not just to sit in front of a computer and type things without understanding what you're doing, which sometimes bring you quite far with interactives you're improving. But ideally, you should understand really, okay, what is an inductive predicate? It's an important concept in computer science if you haven't seen it already. Okay, so now we're going to write some little proofs. We're going to prove that 4 is even, and here I'm going to do it in several steps. So I first prove that 0 is even, then that 2 is even, and then finally I show that 4 is even. To prove that 0 is even, I just use even 0, right? That's the lemma here, right? To prove even of 2, I use add 2 of even 0. I don't need to specify the value here, but I could, right? It's 0. Because you see, add 2 takes a natural number, which is the recursive call here, and it takes a proof of the that this is even before it goes to more. So here we pass even of 0 to get even of 2. We pass even of 2 to get even of 4. And notice here, I mean, this is also very similar to an inductive type, right? I mean, this could be 0 for natural numbers, and this could be maybe the successor function, except that it wouldn't have this argument here. And indeed, proofs, again, proof terms are just terms, right? So what we have, in some sense, what we have created here with our inductive predicate is also a data structure, the data structures of proofs of evenness, right? And here we're saying, well, there are two constructors to this type of proofs of evenness, and this is the first constructor, and it just gives it to you with this type, and this one gives it to you with that type. But you notice the type is you see, it has different values here. So it's a dependent inductive type, just like a vector at the end of lecture 4. So you see, this is very similar to the optional part of the previous lecture, which means, what you didn't learn back then, if you didn't learn it, you're going to have to learn now. So it's really a trade-off. Okay, but with inductive predicates, you have no choice. You have to go dependent. I mean, the whole point of the predicate is to be able to write different values here. So in that sense, they're a bit different from most data types or inductive types where you don't necessarily need that, where you're just like, well, this creates a tree and this creates another tree, and we don't need to distinguish them. But here we really want to distinguish them. We want to know exactly which numbers are even and which are not. And when you prove something, you want to know, is it a proof of even of 2 or is it a proof of even of 7, right? Which would be very worrying. Although a person who says that, you know, said that 5 plus 5 is 25 a couple of lectures ago. So, you know, I shouldn't be judging. Okay, and then the question is like, why not just define it recursively, right? Like this definition here. And yes, there are advantages here. This is going to, and I'm using bool now. This will compute better when evaluating it. But you see here, have to specify the one case, right? So this is true, this is false. So there are 3 cases instead of 2. Also, well, for even, I mean, neither of these 2 versions is the right thing. I mean, what mathematicians would do is this version here. They would just use the modulo. So if k divided by 2 is 0, no, modulo 2 is 0, then it's even. And you would define odd as not even, or as k modulo 2 is equal 1, or something like that. So this one is a toyish example, but it's the ultimate toyish example that everybody uses, because it's actually very intuitive and very useful to you know, get started with the concept. I'm going to show some more examples. The second one is tennis games. So suppose you were to model scoring of tennis. You know, it starts at 0-0, and then it's 15-0, and then 30, or maybe probably they say O or love or whatever. They have weird names for their states. So these are the possible states. You can have 2 numbers together, like 15-15. That gives you a score. Advantage server, advantage receiver, I think it's called. And then you have game, which is when you win, server or receiver wins. And I'm going to use the, what's it called? It's an n dash as a score separator, so it's not a minus. And this is a whole transition system, right? So I'm saying from you know, a 0 state on the left, I can reach 15, right? So that's basically the server that scores the first point, server scores the second point, server scores a third point. And then, you know, if it's 40 to something else, which is lower than 40, then you can go straight to game, you can win immediately. If you're at 40-40, you can go to advantage server. From advantage server, you can go back to 40-40. Same thing with receiver, right? So let me see. I'll try to share a different screen with you. There. So no, this is not the screen I wanted to. Bring your share screen in front. Oh, there we go. Okay. So yeah, this is from my master's thesis. Actually, I like to use tennis as an example, tennis scoring. So it's the same idea here. The names are a bit different. This was a different language. It wasn't lean, but you see these are the possible states when you start at 0-0. This is a whole system, and deuce is just a 40-40 according to our convention. We don't have a special name for it. But so you see, this is what we could draw. But the nice thing, you know, about lean here is that about inductive predicates, it gives us a nice language to specify such system, right? Nicer than the official rules of, which are, let me find them. This is from the guide, right? From the official rules of tennis, sorry. And there's lots of blah, blah, and so on. But then we're not sure what do they mean exactly sometimes, right? And so let's see, resume share. No, sorry, I need to new share, I think. Let's see, I need to go back to my code. There we go. So you see, this is a nice little system. It's actually fairly realistic in some sense. I doubt that people would do much with tennis and the theorem prover because the properties are fairly trivial. But you might have a more subtle system where the properties are not so clear. And what do I mean by properties? I mean is this transition system confluent? So that means, you know, when you take a transition, can you always reach whatever states you could have taken, could have reached if you had not taken the transition? And the answer is no, because you have two separate final states from which you cannot come out. So that means if you take a wrong turn, if you win, you cannot undo that, right? So there's no way to undo. That means there's no, it's not confluent. Does it always terminate? Again, it's pretty obvious that no, you can, you know, enter a loop and so on. But here, you know, we can specify this formally. We can write a lemma that says this is not confluent, or this is not terminating, and so on. Or the score 65-15 cannot be reached, or all scores that are reachable are of the form such and such, right? So we can state various lemmas, which for tennis are obvious because we have watched too much tennis on TV, presumably, right? But again, it's very typical of other transition systems as well. So it's a good example, I think. The reflexive closure is really the star when it comes to, oh, and that's even a pun because it's called star, but when it comes to inductive predicates, wasn't intended. So transitive closure means, oh, did I say there would be 4 examples and we've seen only 1, 2, 3? Okay, well, okay, that's so much for, oh, there's a non-example coming. Okay, that counts as the 4. So this one is really nice. So closure is this idea of you take something and then you add stuff to it until you cannot add stuff anymore. So reflexive transitive closure means that you take an existing relation and then you make it reflexive and then you make it transitive on top of that. But you want to have the smallest relation, you know, the smallest extension of your original relation R that is reflexive and transitive, right? So reflexive just means it's going to be that you always have, well, you see it RAA. So if you don't have RAA and RBB, you know, if something is not in relation with itself, then we make it in relation with itself. And if something is not transitive, you know, we can go from A to B and B to C, but not from A to C. Well, we add that edge, you know, missing edge A to C. So this is done, you see, using star, because the notation in mathematics is a star, is a little exponent, a Kleene star, I think, or and it takes, of course, a type, we don't care, a relation R, which is really a binary predicate, right? So it's not technically a relation, but it's isomorphic to a relation. We're going to call it a relation. That makes it simpler. A relation would be a set of pairs, but a set of pairs and a binary predicate are isomorphic, so we're just going to call it a relation. And star, the result has the same type as R. So you take R, which has this type, and you return R star, or star of R, which has the same type, but it's kind of repaired so that it's reflexive and transitive. And then we have 3 cases. The base case says, well, if you could do a transition with R, you can do it with star of R. Here we don't put the R as usual because it's a parameter. It's on the left-hand side here of the column. We make it reflexive by saying, you know, for all A, you have star AA, and then transitive for all ABC, you have if star AB, if star BC, then star AC. Okay, and here I claim that this is truly elegant, and if you don't believe me, you can try implementing it with a recursive function. If you want, you can replace the props by bool here. That would make it more computable, maybe. But then you'll see that it's quite nice to be able to just state things as rules without worrying about things like, oh, in which order should they be executed and things like that, because these rules, it doesn't matter. I can also write them like this. It changes absolutely nothing. So each rule, you know, is independent of the other. Just like the typing rules we saw in lecture 1. And in fact, that's a very good example because typing rules are essentially inductive predicates, but, you know, at a different level of abstraction, right? So, you know, there's no predicate called, you know, typing rule in Lean itself, but the theory of Lean, or the meta theory, I would call it, is justified using say, inductive predicates and similar concepts. right? So basically, whenever you have like a system with these horizontal bars in it, then that's, you know, probably just a fancy LaTeX representation of an inductive system. Okay, and here's the fourth example, which is a non-example. So here I'm not very careful. I'm trying to create illegal 2. We saw illegal, I think, in last lecture. So this is its call. But we're saying, yeah, we're saying if not illegal 2, then we make it illegal 2. But at that point, that condition is no longer met. So it's kind of an if and only if, actually. We cannot create an inductive predicate like this quite simply. Right? If we had, you know, we had in our hands, you know, a value that says illegal 2 is true, then we could look at this proof and obtain that it was created by having not illegal 2, and from this we would derive a contradiction. So Lean gives us a very, I'm sure, helpful error message. It says arg number 1 of intro has a non-positive, which is misspelled, by the way. There should be no space or hyphen there. Occurrence of the data types being declared, right? So data type here actually means inductive predicate, but by Curry-Howard, it's the same thing. So non-positive means basically that, yeah, we have negation, which is kind of a minus, and Lean doesn't like that. And this is correct. We would run into trouble if we didn't stop that. So I'm not going to try to axiomatize it and derive false, but you can trust me, this will also not end well unless our goal is to derive false.